All right, testing. All right, let's get started. All right, hey guys, I'm Tom Huynh. So try to reach out to your pocket right now, and hopefully your phone's in your pocket. You can see that your phone is so convenient. That's why you bring your phone everywhere with you. It do a lot of things for us, right? It check the weather for you. It turn on the alarm for work. It can check your social media, connect us with your friends, family. But there's one thing that our phone cannot do yet, which is telling you how do we feel right now, right? So, hey Siri, how am I feeling today? Okay, Google, what are my emotions today, right? These questions seem to be really silly, but with the advancement in sentiment analysis and machine learning, this is actually possible right now. So, hi, welcome to the workshop of sentiment analysis with TensorFlow. So if you are not the expert of machine learning and AI, so don't worry about it, right? So we're gonna teach you the intuition of the concept for this topic because we are aware that a majority of you guys are students. Also, I'm gonna show you how to code it by line, all right? And also provide you extra material after lectures for you to do your own research. Sound really fun, right? Before we get started, so let's introduce you guys. Let's meet Tom Huynh, right? About me. Okay, so currently I'm the director of machine learning at Coder School. Previously, I'm the former head of web development at Web Optimizer in Melbourne, Australia. Also, I'm a Google certified TensorFlow developer from deep learning and machine learning. I did my master in AI and machine learning in Sydney, Australia. And also I finished my bachelor's of computer science in Melbourne, Australia. I love competitions. I joined different startup AI tech hackathons and I won a few. Okay, so that's enough about me. Very nice to meet you all. I want to share with you guys some insights about this interesting topic, which is sentiment analysis. But by now, you might asking that, like, I'm working for Coder School. So what is Coder School, right? So let me tell you guys a bit about Coder School. So Coder School is the organization that drive the frontier of technology in Vietnam through education. We provide both online and offline coding courses, mentorship, job placement for our students and alumni. So if you have no experience in coding, you want to learn about coding, or you want to improve your current tech skill, then you can start the tech journey with us. We have two main subjects, data science, machine learning, and web development. For machine learning, we have a data science courses with the different flexible options for you guys. Can be online, can be offline. You want full-time or part-time, no problems, right? And also we have a short-term course for the data analyst for part-time people, right? We got to cover. For the web development course, we have similar options, right? Online or offline, full-time or part-time. So we are very serious about our job. So we're going to promise our students that with 100% job guarantee, because we have up to 200 hiring companies in Vietnam. We have a dedicated team for student outcomes. We're going to support you for portfolio. We're going to support you for resume, final project. We also help you guys with the interview questions so you can land your dream job. In short, if you don't know where to start, Coder School will guide you from the start to the end. So there's a variety of natural language processing techniques out there, but the one I'm talking today in the workshop will be the sentiment analysis. Here's a few key takeaways from today's workshop. Firstly, I want to talk about what is sentiment analysis, right? I'm pretty sure that most of you guys are like, hey, what is sentiment analysis? It sounds like rocket science. Secondly, I would like to talk about why it's so important to business and society. Thirdly, I want to talk about the general pipeline to processing the text for the computer to understand what is text. Fourthly, I would like to talk about the tokenizations. It's a step to represent words for the computer to process before the machine learning part. Fifthly, we talk about the word embedding vector, gonna enhance the meaning of the tokenizations. Really cool. I think one of the most coolest things you can learn today's workshop going to be the word embeddings. And lastly, we're going to talk about the deep neural network. And I've got a surprise for you. We're going to have a really special lab today. Okay, it's going to be hands-on. Do you need to code along? So someone asked me, do you need to code along? Not really, because as my calculations, right, the workshop will be exactly 2 hours. So definitely you guys have no time to code. But don't worry, I will prepare the code for you guys. I comment every single line of code, and we go through line by line for you guys to understand. Because at the end of the day, who cares about like coding live anyways? Because you can search for the answer online anyways, right? So it's more important how you understand what is this code for. So I will go through line by line for you guys, so don't worry about that. It can be extremely intuitive and easy. Okay. I know that right now the agenda look like to learn the rocket science, but trust me, it's actually quite straightforward as long as you follow the lectures. Yeah. All right, so let's think about a real world challenge for today. Okay, let's think about a scenario. So let's say you are the manager of a company that's selling hats and also shirts. Sorry. Okay. Okay, let me put a shirts and hats on the guy. All right, beautiful. Okay, so your company only have two products, hat and shirts. And and then you want to know that do your customer have a positive feeling about them or negative feeling about them, right? So what you can do is you can go to the call center and you can check out your social medias, right? And you can see that a bunch of people have coined or post on social media about the products, right? The hats and the shirts. So you want to figure out, hey, what's going on? So you can go through these by listening or reading every single message. That's gonna take you forever, right? For your information, 90% of the world data is unstructured. This means that it's super unorganized. So there's a huge volume of unstructured business data that create every day. For example, emails, support ticket, chat, social media conversations, survey, right? Articles, documents, right? So it's really hard for anyone, so for the business owner to analyze a sentiment in a timely and efficient manner. So instead, you're going to use a machine learning model to go through and tag these as a positive and negative comments about your products. And at the end of the day, after you apply your machine learning model, you figure out that, hey, people tend to think that your hat is pretty good and your shirt is not good, right? So without you have to go through that in real time. So you can like maybe producing more hat to sell and maybe figure out what to do with the shirt. You can stop producing shirt anymore, or you can try to improve the issues regarding that. So this concept, we call them a sentiment analysis. Try to figure out the emotions of the text. So let's go through the definition, the real definition of the sentiment analysis, right? So sentiment analysis is the process of determining the opinions or the feeling of the piece of text. This could be like positive, negative, or neutral, right? Or it could be a feelings or emotion like angry, happy, or sad. Or it could be like urgency or not. It could be about intention, right? Interested or not interested. So the output of the model depends on the task you want to achieve, right? And sentiment analysis is one of the hardest tasks in the natural language processing, because even human, we are struggle to analyze sentiments accurately, right? For example, yesterday was the International Women's Day, right? And you take your girlfriend to buy a bag, and your girlfriend told you that this is better than nothing, right? This is better than nothing. So at least there is a word better, but she compared that to nothing. And then the boyfriend was thinking, hey, is it a positive or negative comment about the bag? This is better than nothing, right? Even for human, we have a trouble to figure out is a negative feeling or positive feeling based on the text. So the machine gonna do a better job than that. That's really exciting. So to let you guys really high up about the sentiment analysis, I'm gonna go through why it's so important. Okay. The first reason why important is brand reputation, product service monitoring, right? So sentiment analysis is extremely important because it can help business to understand the social sentiments of the brand or the product or the service while monitoring the online conversations on the social medias, across the internet, on the news site, blogs, forum, product reviews, and more. For example, you can use sentiment analysis to analyze thousands of reviews about your products. That could really help you discover if your customer are happy about your pricing plan or customer service, right? So again, we can look at not just the volume of the mentions about your brand, but also the quality of the mentions. Are they happy? Are they sad? Are they angry? Is there anything we can do about it? Next up, we're gonna talk about the customer service. All right, this is a huge thing for the sentiment analysis. Let me explain why. So let's have a look at this one. Okay, I'll let you guys spend like maybe 1 or 2 minutes to look at this. Okay. Okay, so for customer service, you guys should know that a better customer experience means that a higher rate of return customer mean bigger profit, right? So customer expect their experience with the company to be immediate, intuitive, personal, and hassle-free. So if not, they're gonna leave the company and do business elsewhere, right? Did you know that 1 out of 3 customers gonna leave the company after just one bad experience? So making the customer happy is really important for customer retention. For example, the first the first girl was bougie, and she was like want the flat rate policy of Uber to be back. Okay, so make Uber rate again. So she want the policy of flat rate to be back. Okay, so that may be one thing that Uber can consider. For example, for the second guy, so there's an issue regarding the system of Uber, right? So the driver cancel on him, but he got charged the cancellation fee. So it's not fair, right? Uber need to take action to fix the system. Otherwise, customer gonna leave for other companies like Lyft. The third one is Postmate, right? So Postmate is the company deliver groceries and stuff. And this person was really unhappy with the customer service, right? It's impossible to reach them. So maybe Postman should do something about it, right? And lastly, about Airbnb. So this person say that Airbnb customer service was totally useless. Okay, that's a big comment. So they should do something about that. So you can see that these not only 1 or 2 or 3, could be a millions of them. It's impossible for company to like look through all of this and figure out, okay, what's the majority issues, right? Because at the end of the day, sentiment analysis can identify the urgent issue in real time. No problem. I can do all of that. I can analyze all millions of comments in real time, in milliseconds, to avoid the PR crisis by taking action right away. So this is a genius idea. Okay, so that's for customer service. And for the market research, sentiment analysis can empower all kind of market research and comparative analysis, right? So you can do the explore a new market, you can anticipate a new trends. You can gain some insight by look into the customer opinions. One, you understand how the customer feel, what they like, what they dislike, and you can build something like recommendation system. You can do something like target marketing campaign for them, right? To target them more. Or you can follow your competitor in real time on social media to figure out that, hey, my competitor released a new product and no one buy them, right? You can figure out what aspect went wrong with that product and use that for your advantage. So that is customer research, really powerful. And lastly, well, the first 3 reasons was for only for business, but the last one is for society. Okay, so let's talk about that. So what is the social purpose? Social purpose can help people with the mental health issues, right? You think about the people with depression, people with bipolar, they spend a lot of time on the internet. So with this technology, we can provide help for the people by identifying them early with some dangerous behavior, right? So we can make the internet a safer place for us. Maybe one day, machine learning model can become a therapist for all of us. So with all these benefits above, I hope you're convinced that a sentiment analysis can make all difference in the world. Okay, that's the power of machine learning, guys. Very exciting. Okay, so you know what is sentiment analysis and you know why it's so important. And now I want you guys to know how to build a sentiment analysis model. Okay, I'm here to help. It's not that hard. It's actually quite simple. Okay, so this is the diagram for the whole pipeline we're gonna build today. Okay, so the first one is the input. which is a millions of text. We can call that corpus. Corpus means collection of text, okay? Customer reviews, customer text stuff. And then to prepare that to be ready for the machine learning models in the third step, we need to pre-processing it. This step actually very complicated, so I'm gonna keep it simple and only talk about tokenizations and paddings. Okay, tokenization is the step that you turn letter or words into numbers, and padding is a step for you to add a bunch of zeros to make sure that all the sentence have the same length. All right, seems really simple. And then after you process them, you plug them into the machine learning model. In this case, we're gonna use the neural network model. All right, we are training guys. We not use an ancient machine learning model anymore, like SVM or logic regression. We are using the state-of-the-art neural networks. Okay, so we're gonna have a quick lectures about deep learning as well. That's really cool. So after training the model for a few times or for the few iterations on the whole corpus, we can use this model to predict a new sentence for sentiments. That's it. As simple as that, right? We can predicting a new sentence. Is it positive or is it negative? Okay, so let's talk about each of the components in the diagram. Okay, so we have 4 components here. And let's talk about the first one, which is input. Okay, machine learning, right? Machine learning need to learn from a data. So let's talk about data. Okay, so first let's talk about our input. So we're gonna using an IMDb movie review data set. Classic, guys, really classic. I hope everyone know what is IMDb. If you don't know what is IMDb, you need to Google right now. Google IMDb movie reviews, because I'm a big Netflix fan, and every time I'm watching Netflix, I always need to check the review first before I watch it. And the first favorite website I check the movie review would be on IMDb website. Okay, it's a website that gives you a bunch of reviews for movies. Okay, so you can know which movie is the best to watch. Simple as that. And there are 2 columns for this data, right? Text and labels, okay? So for the training, we have around 25,000 reviews, okay, from different users, okay? And for our labels, what is the expected output? Would mean that we hope that after our machine reading these reviews, text, the machine would like predicting that, hey, it's actually a negative review. Or if the machine reading this review, I hope that it's gonna predict it's a positive review. Okay, as simple as that. So this is extremely important because we want the machine to mimic that, to say, hey, this is the right output. I want you to get this output. Okay, extremely important. 0 mean a negative review, and 1 mean positive review. All right, super simple. And then, okay, this information is crucial for our training. Okay, and then to be a good data scientist, we need to split the data, right? 1 for training, 1 for testing. I will not go too much about this. The idea we split the data because our model only supposed to see 1 part data. And if the model are a bad model, a naughty model, the model gonna memorize every single text here and say it's 0, or memorize every single text here and say it's 1. We don't want that. We want the model to be able to generalize well. That's why we have another 25,000 review just for testing. Just to say, hey, these review you haven't seen before, can you predict them correctly? Yeah, this is the ultimate test. It's like in the exam, right? If I give you the practice question the same with the real exam question, there's no point, right? You just copy and paste, right? I want the question to be different. The same thing why we have to split the data for training and for testing. Okay, this is extremely important. I can talk about this topic for like another 3 hours about what is the best way to split the data, but we're not gonna do that. Okay, so you know that movie reviews are a bunch of text, a bunch of string, a bunch of words. How do you convert them into numbers, right? Because at the end of the day, the machine, the computer can only understand numbers. Okay, so straightforward. We need to figure out how to convert string or bunch of string or a sentence into numbers. Okay, so let's try that. Okay, so there's two strategies to do that. So let's talk about a new term here, mean tokenize. What does it mean by tokenize? So tokenize is a process of encoding a string of text into numbers. So that later on, you can use a neural network to understand the meaning, okay? So this process called tokenizations. So right now, let's talk about there are two possible strategies to tokenize a sentence. It could be letter by letter, or it could be word by word. Which one are actually better, right? So let's discuss the first way first, which is letter by letter. Okay, we try to tokenize a word letter by letter and see is it good or not. Okay, so let's start with a very naive way to tokenize a letter to be understood by a computer. Um, okay, I can't make a poll here. I wish I want to make a poll here on Zoom that how many people here actually know about ASCII2 encoding table. So for the computers right now, everyone know like what is Unicode, right? Unicode is like a universe of uh, encoding font that understand all the languages. So technically, Unicode is the extensions of ASCII2. Okay, ASCII2 only for alphabet, English alphabet characters. Okay, so we're gonna use the ASCII2 as the a standard way to encoding our characters. Okay, as simple as that. Okay, you can see that these letters can be represented by numbers using this encoding schema. Okay, so we're gonna have a game here. Okay, so you guys consider the word listens. It just make up a bunch of letters. So using this ASCII encoding table, can you figure out a way to convert this letter into a sequence of number? Okay, give you guys like 2 minutes for that. I'm very generous. So spend 2 minutes, maybe write on your papers. Um, what is the sequence of numbers this work representing? Okay, I hope makes sense. Okay, go 2 minutes. Okay, exactly 2 minutes. I come back, and then I give you guys the answers. Okay, you can see that I put a timer here. Okay, 2 minutes. Let me repeat the question again. The question is, how can I convert this letter listens, LISTEN, into a string, a sequence of numbers using this ASCII encoding table? You can see that it's really simple. You convert each letter into a number. And let's see if you can figure out that. Meanwhile, I try to answer the questions in the chat. Sorry, it take me forever to answer questions in the chat. Okay, the answer is okay. L is 76, I is 73, S is 83, T is 84, E is 69, and N is 78. Correct. So I saw a bunch of people got the correct answer in the chat. Good job, guys. Perfect. Um, Interesting. Let's try another example here. I'm not gonna waste the time. I'm gonna give you the answer right away. This will be 83, 73, 76, 69, 78, and 74. Okay, you can see that it's made up of a sequence of letter. Okay. Um, okay, so why I'm choosing these two specific example? Interesting, because if you look at that carefully, you can see that for these two example, have the same numbers of they have the same numbers of okay, they have the same sequence number of numbers, and they, even though it's not in the same orders, but I know that they are the same collections of numbers. So there's a problem with that, right? The problem is the word listen and the word silent have the same letters. So that's why it have the same numbers, just in a different order. So unlike words, right, character doesn't have any meanings, right? So there's no guarantee that the result of this tokenization will be meaningful. So we gonna run into the problem later on that this method gonna struggle to recognize the semantic or the meaning similarity between words. It's gonna make it really hard for us to understand the sentiments or the meaning of the word, just the letter in it, right? So from the start, this method is doomed. The second disadvantage is it cannot increase the input computations, right? So let's assume that a sentence got 7 words, and each word gonna have an average 5 letter, right? So in total, you're gonna have a 35 tokens or 35 inputs to process, right? This can increase the complexity of the input for the model to process. But if you tokenize word by word, so 7 word sentence gonna have exactly 7 input tokens, much smaller for the model to process. So you can see that there's a bunch of problems with the letter tokenizations. So let's discussing the word tokenization. It means that tokenize word by word. Okay, for example, this. So instead of encoding a letter, I'm gonna encoding words. Like for example, consider a sentence, I love my dogs, right? So what happens if we encoding the word in the sentence instead of the letter of each word? Then I can have the word I is 1, the word love is 2, the word my 3, the word dog is 4. So 1, 2, 3, 4. As simple as that, right? Let's try another example. Let's say that is a sentence, I love my cat. So how would we encode that? You can see that I love my already 1, 2, 3. All right, so you can guessing that I love my in the second sentence gonna be 1, 2, 3, but dog already 4. Cat is a new word, so it's gonna be 5. Yeah. So right now, if you look at 2 sentences, there are 1, 2, 3, 4, and 1, 2, 3, 5. You can see that it's got 1, 2, 3, the same. It already shows some similarities between them. That's good, right? Because it's a similarity that you would expect. Because both of them is about someone loving a pet, a dog or cat, right? So now you have seen that how the words can be tokenized. But guess what? Nothing is perfect, right? Even word tokenizations is not enough. Just like real life, like so how can we improve? What is the problem with that, right? Let's have a look at the example. In this example, I changing my second sentence a bit, right? My first sentence will be, I love my dogs. The second one will be, I like my cat, right? We have 2 new words in the second sentence, like and cat. All right, so love is 2 compared to like is 5, dog is 4 compared to cat is 6. So you can see that this numeric encoding is a bit arbitrary or randoms, right? We treat every single word independent with each other. and does not capture any relationship between words. For example, it's actually struggle to recognize the semantic or the meaning similarity between words, right? For example, it's fair to recognize the similarity between the word love and like, because it treats these two words independently, right? Love is love and like is like. But you know that they got some similarity, right? Love and like very similar. But we treat them 2 and 5 totally independent. And similarly to the word love and hate, gonna be independent, right? But you know that they are opposite. So we want to capture this relationship between words. And word tokenizations not good enough. So how can we improve our word tokenization so that it can capture a relationship between different words? All right, now it's getting interesting because we need to add word embedding vectors on the top of our word tokenizations. Okay, let's show you guys example. So you might wondering at this point, right? So we have turned our sentence into numbers, with the numbers being tokens representing words. But how can we get meaning from that, right? This one doesn't have meaning, right? You can see 1, 2, 3, 4, and 5 doesn't have any relationship. It cannot capture a relationship between words, all right? So how can we do that? How can we get the meaning from that? So how can we determine if something positive or negative just from numbers? So that is exactly the context of embedding vectors come in. So let's consider the most basic sentiments here. So something is good or something is bad, right? Okay, so for example, good, we can have that on the right hand side, pointing to the right hand side. And something is opposite or bad can be plot them in the opposite directions like this. Okay, and the phrase okay, I use okay a lot, so let's use the phrase okay. For okay, right, it means something good, but not that good, right? It's okay, it's not that good, and also not bad. So I plot them to be like that. It got a big of goodness. And what about the word unexciting, right? It's not good, it's not bad. So for example, if you went on a date and someone told you that, hey, you look unexciting, it's probably negative, right? But it's not that bad. It's like you're not exciting. So it's probably bad more than good. So you can plot them like that, okay? And now you plot this on the X and Y axis. You can start to determine the good and bad sentiments at the coordinate in the X and Y. Okay, good is 0, 1. Unexciting is like negative 0.5 and 0.8 and so on. Now consider my sentence. Okay, this is Tom's sentence in the movies. I say, okay, but unexciting movie, for example. Is it good or is it bad, right? Now you're thinking, hey, is it, what does this mean? He mean positively or he mean negatively? This is really confusing for humans, right? But for a computer, no problem, right? How do we do that? We're just gonna sum up the factors of okay and unexciting and take the average. Okay. So the output of the sentence of okay and unexciting gonna be somewhere between 0.7 and 0.1. Okay. So that's sentiments considered to be slightly on the good side of neutral. Okay, based on our vectors. So similarly, the word appear in the negative sentence going to have a strong component in the negative directions. Okay, vice versa, right? Sentence like words appear in the positive sentence going to have a strong component toward the positive directions. Okay, straightforward. So by looking at the direction of the vectors, we can determine the meaning of the words. Okay, so this concept is known as embedding. Or I swear to God, guy, this concept take me like 2 months and you need to understand this. And you guys have this for free, so be grateful about that. Just kidding. So what embedding provide us a very efficient way to determine what is a similar words, right? And the similar words tend to have a similar encodings. All right, the question now is, you can see that this plot on 2 dimensions. What if I extend that into multiple dimensions instead of 2, right? Exciting, like, oh my God, like that's what kind of question is that? Yeah, it's actually possible, right? Before we have 2 dimensions, good or bad. Now let's extend that into 4 dimensions. Ooh, curious. Gender, royal, age, and food, right? These are 4 dimensions. You can say that it's like 4 aspects describing a work. Okay, so these 4 aspects describing these work we have. So we have these work like man, woman, king, queen, apple, and orange. Okay, so each of these work gonna provide. Okay, I'm gonna draw. So each of, let's say for example, the work man here gonna be represented by the vectors, these 4 numbers. The work woman here gonna be represented by these 4 numbers, because these 4 numbers is representing an aspect of that work. Wow, this is really cool, because to understand the work, right, you don't need to read a definition of the dictionary anymore. You can just look at the vector and figure out. That's cool. So let's quickly go through that. So for genders, we have man to be -1, okay, very manly, and woman to be 1, mean very feminine, and king definitely a guy, so definitely pretty negative number, close to -1, and woman is a female, so close to 1, and apple and orange are fruit, and you don't really have gender in fruit, right? So nearly close to 0. Royal, everything will be 0, nearly close to 0, apart from king and queen. Age, when you talk about men and women, they are pretty neutral when it comes to age. You can't really determine their age, right? But for king and queen, to be a king and to be a queen, that definitely they need to be more mature, so high numbers. And for apple and orange, close to 0, because there is no age when it comes to the work fruit. And fruit, right? And everything will be close to 0 apart from apple and orange. Now you can see that by having the aspect, the dimension, you can describe an attribute of features of a word. This is really interesting. Um, so if I put the word apple and orange into my model, I want these vectors to be very close to each other, right? Because these are related words. They're both fruits. So this kind of representations make it possible for words to have a similar meanings, to have the similar representations, right? Which can improve our model performance. Now, some people are gonna ask me in the chat, right? Okay, so what is the common numbers of dimensions I can representing for my vectors? It's actually up to you, right? But consider these thumb rules. So it's really common to see the word embedding that 8 dimensions for a small data set, and up to 1,024 dimensions when you're working with a really big data set. The higher dimensions of the embedding can capture more details of relationship between words, but it takes more data to train, right? Importantly, you don't really specifically go through this by hand. Think about that. You have 10 million words, and you can have up to 300 dimensions. Who have time to go through and enter numbers here by hand? No. Cool thing is, these are trainable parameters in our model. So the machine is gonna look through these sentences. Like we have 25,000 sentences in our MDB database, and the machine is gonna figure out what is the best number for that. Like magic, right? It's like, wow, really cool. So this is how machine understand the definition of the word. Wow. Okay. So for humans, this is really interesting. Like this is not how we see words. We have to read definitions of the word in dictionary. But for machine, this is perfect for them. It's just numbers. They're good for that. Okay. So here example to prove to you that this word embedding can capture semantic or meaning relationship between words. Okay. So let's plot the word embedding of queen, king, woman, and man into these 2-dimensional space. And these numbers are already trained in the embedding layers after the model is trained, right? So these numbers are good. Let me ask you questions. Okay, let me think. Let me paraphrase the questions. If someone is a king, but not a man, who is a woman? So who is that? Okay, let me paraphrase that. If someone is a king, but not a man, but is a woman, who is that? Can you put in the Q&A? Or we can describe that into math equations like king minus man plus woman. Who is that? Can you put in the chat, please? Oh, Jesus Christ. People are enter. Oh my God. People are creative. I saw a few offended and funny answers. I like that. But I'm not going to share you guys. It's not appropriate. Yeah, all right. Oh my God, that's good. Okay, so most people say that it's queen, all right? It's a queen. Come on, it's a queen. It makes sense, right? King minus man, not a man, but really royal, plus woman is a queen. But can I prove that? Can I answer that by do some math? Do some like simple math logic or vector additions? Okay, let's consider this. So we have these original vector, the relationship between man and woman. You can do that. You can do the subtractions. And when you add these two, you can shift the vector, right? So you add them together, give you a new vector, and the new vector very close to queen. Okay, so you already proved that this actually a queen. But the cool thing is these vector king to queen, man to woman, actually encoding genders. Oh my God, that's so cool. So you can do uncle, aunt, son, daughter, king, queen. Let's say this direction is more feminine. And this direction is like higher status, right? More royal. So these encoding actually got some encoding some relationship, some meaning. Oh my God, this is really cool. It's like, this is how computer understand our language, right? Oh my God, this is really cool. So the first time I saw this, I'm like, wow, this is shocking cool because you can do some math with language. Yeah, that's weird, right? So when you study literature in your school, right, you cannot expect to do math and to be good at literature. Now you can. Now, if you're a good data scientist, maybe you can generate your essay. You can even finish your uni essay, just by being good at computer science. So there is a story that with the new model GTP3, you can generate a convincing university essay, apply that and submit that to the lecturers, no problems. All right. So the world has been changing. So let's talk about relationship in word embeddings. Okay, so the same logic apply for other relationship, right? So the difference on relationship between men and women is the same with relationship between king and queen. All right. And relationship between working, right? It's a present tense, and worked is a past tense. It's like relationship between swimming and swam. Okay. And relationship between capital city and the country is like Vietnam to Hanoi. It's similar to Japan to Tokyo. It's similar to Germany to Berlin. It's similar to Italy to Rome. That's really interesting. Okay, so a computer can understand this relationship already. This is how the machine understands the concept of relationship in words. This is quite amazing because human understand relationship in the words. We need to read the definition of the words in the dictionary. But for machine, no problem. I can do that pretty well by encoding them into vector number, just like that. Oh, all right. That's pretty sick, I guess. And here are the real life example of 10,000 words that have been trained for 200 dimensions, right? For the purpose of visualizations, I'm using PCA to reduce 200 dimensions into 3 dimensions to show you guys this. Each of the dots actually embedding vector for our work in 3-dimensional space. So you can link to this link here to check it out. That's really cool. But is there anything that we can learn from this? I can show you an example. So today in the lab, you're gonna build your sentiment analysis model. And after you train your model, you take out the embedding layers, you plot them into the 2D math, and you figure out, hey, I want to know what is the work, where is the work wonderful, and where is the work horrible. And the surprisingly result is they are in the extreme size of the sentiments, right? They are on the different side of the spectrums of emotion when it comes to negative and positive. So, so you can see that wonderful is one of the most positive work you can give beside excellence, right? And horrible is one of the most terrible work you can give to the movie. And they are presented in a different size of the spectrums of emotions, sentiments. And that is so cool, right? And we have these 10,000 words. Think about that. Uh, so if you ask someone that, can you figure out how bad or how good is the work? Take them a long time to do that. But the computer can do that in no time, right? So now the computer understand what word is contribute to a positive or negative feeling inside a sentence. So I really recommend you to stay tuned until the end of the workshop so we can go through this together. The other cool thing is, what about the word embedding in the general data, right? So you can see that these country words like Poland, Greece, Russia, Austria, Turkey, Brazil, Mexico, right? These are close together in the word embedding space. The words have a similar meanings, tend to be together because they share the same context. And similarly to the states in Australia, in America, right? We have the Colombia, we have Florida, we have California, we have Virginia, we have um, Utah, right? These are close together in right here at the corners here. Okay. For example, these are the months of the years. They appear oftenly in the same context. They got similar meanings, so they are in together in this group. All right, so that's pretty cool. So with this, I'm pretty sure that I can plug them into my machine learning model, and my model can figure out how to determine what is the sentiments of a sentence. Okay, so that is a big rocket science, but I want to sum up what is the pipeline, how tokenizations and word embedding gonna fit together inside our model. Okay, so you can see that there are two sentences here. The mouse ran up the clock and the mouse ran down, right? We have two sentences. Different sentence after tokenizations, they're gonna have, it's gonna producing a dictionary, right? Dictionary here, gonna mapping a word, a unique word to a numeric tokens. Let's say the is one, mouse is two, run is three, up is four, block is five, down is six. And using this dictionary, now you can go back and encode the sentence. Like for example, 1, 2, 3, 4, 1, 5. Okay, let's decode that. So 1, D, 2, mouse, 3, ran, 4, up, 1, D, 5, clock. Okay, so using this, you can decode back to the original sentence. Similarly, we have the mouse ran down. After you encoding them with tokenizations, it gives you 1, 3, 1, 2, 3, 6. Okay. Each of these, like we discussed before, is a word tokenization. It's just a number, right? We want to add some meaning into these numbers. So each of these we want to convert each of these numbers into a vectors. And we happen to choose that dimension to be 4, right? So each of these word tokens gonna give you back a 4-dimensional vector. So for example, 1, 2, 3, 4, 5, 6. We have 6 words in the sentence. Give you back what? The first one here, let me show you my drawing. So the first number 1 here is this vector, right? And the 4 here is this vector. Do you noticing that? Because the next one is number 1. So the vector, the next vector is the same with the first vector, right? Because they're both representing for the word the. Okay, this one also the. So for each of these numeric tokens, we convert them into a word embedding vector. And each of these vector contain 4 numbers because we choose that. four dimensions. Okay, that's pretty straightforward, right? And you can see that we have four work here. It gives you back four, 1, 2, 3, sorry, 6, right? 1, 2, 3, 4, 5, 6. Give you back 6 vectors embeddings. 1, 2, 3, 4, 5, 6. Okay. Similarly, for the second sentence, you got 4 words. If you back 4 vectors. Okay, so straightforward, pretty straightforward. Okay, so want to let you guys know is that these numeric numbers at first are totally randoms, right? So the numbers, the value inside these embedding vectors are totally randoms at first. After you fit these numbers into our models, the model gonna treat these numbers as a trainable parameters, right? It's gonna update these numbers at every single iterations during the training until it's very good at the task, with it predicting the sentiment of the sentence, right? During the training data set. You will see that we're gonna use TensorFlow to get this done effortlessly. That's why we need to pray to our God of TensorFlow, like creating such a wonderful framework to make everything so easy to get done. Look like rocket science, but trust me, the coding will be so simple. All right, so you can see that after this part, right, after you get back the embedding vectors, what next? We need to fit them into, okay, let me go back to the diagram from beginning. We need to fit them to the training machine learning model. Okay, so let's talk about that. Okay, so what is the machine learning models? Okay, bear with me for a few minutes. I'll quickly go through what is machine learning, what is deep learning in maybe in 5 minutes, and then I'll let you guys have a break, quick break for 5 minutes, and then we're gonna go through the workshop, yeah, the lab, exciting stuff. So you can have a break later on. So try to be focused now. I know it's big, long. Okay, so machine learning is simply like math functions, right? You give it one of many numbers, you plug it in, and then the machine, the model, gonna give you back one of many numbers. At first, the result is pretty bad, okay? And then after many iterations during the training, it's gonna update the parameters so that it's gonna give you back a number closer to what you expect. So after the training, you can use the model to predicting a new sample. So the idea is very simple, right? You plug in numbers, you get out numbers, you keep doing that, and the model try to like figure out, hey, what is the right parameter to map that input to the right output, and that's it. That's machine learning. You use data to train the model, and the model will update the parameter to give you the expected output. Okay, that's the idea of machine learning. But today's workshop, I'm gonna focus on the cool new stuff, which is deep neural networks. It's pretty cool. This is what deep learning have achieved since 2010. Okay, I'll let you guys like 10 seconds or 30 seconds to read through these collections. Fun fact, I spent like 45 minutes to make this picture. So you should be grateful about it. And I haven't had dinner yet, so okay. I'm gonna do everything for machine links. Be like machine. All right, so let's go through this. You can see that this is what deep learning have achieved since 2010. All right, machine learning, deep learning beat humans in games like Star Wars 2. And also, machine AI can outperform human lawyers in terms of reviewing legal documents. That's crazy. It's replacing jobs. A lot of people want to run out of jobs, you know. And then also machine and AI, deep learning can beat human in trading. Oh my God, the machine will be rich. And also it beat human in Go, in ball game. Oh, Jesus Christ. Do you know that the combination of the move in Go game is more than the atoms in the whole universe? And deep learning beat humans in that. And also, machine learning model can beat human in object detections. That's crazy stuff. Also, AI can beat human in the poker games, in card games. Now, deep learning model can have a new human conversations, right? So they said that this chatbot is so good that you can't recognize between humans or machine anymore. Because I remember in the article they said that this bot are actually more interesting than most people in the world, because most people in the world are pretty boring, right? They can't make jokes, they don't have that great personality, but this chatbot is positively built to accommodate humans, so it know how to make jokes, it's very friendly, this and that, right? So maybe in the future humans gonna prefer to talk to the chatbot than real humans. And lastly, the deep learning model with human in reading tests. Oh my God, this is crazy, man. This is exactly why I spend a lot of time in machine learning, deep learning, because I believe that in futures, deep learning gonna provide more benefit for humans. Yeah, for sure, gonna change everything. The question now is, what is deep learning? So deep learning is different from machine learning. Yes, deep learning actually a machine learning model that inspired from human brain. That's crazy. That's why it's so smart, right? So let's have a quick biology lessons here. So this is a human neurons. Okay, I try to be a good teacher in biology. So you can see that this is dendrite. Okay, this you call that these input, these branches. So technically, at the end of the day, there's a signal coming through the dendrite as the input, and then the signal going to be processing in the axon. So axon, consider that to be like a CPU, like a processing unit, right? If the signal is stronger than a certain threshold, it's gonna fire a signal out to the synaptic terminal as the output. Okay, that's it. And then if you connect a bunch of them together, you're gonna have multiple layers of human neural networks, the brain. This is exactly in our human brain, right? And the deep learning actually inspired from this um, biology masterpiece. So that's pretty cool. That's why deep learning is a bit scary. Like, hey, what's going on? But it's actually not that scary. I give you an example. This is a simple example of neural network. So we have for input the origin of the airport, the destination of the airport, the departure date, and airline. This is the input, right? And then you're gonna build a neural network like this. And I won't talk too much about the details, but at the end of the day, it's gonna just the linear combination. It's a math. It's a linear math, and the output will be one single numbers. Okay, to predicting the price of the ticket given for input, and then the model give the wrong price, right? And you say, hey, the correct price is this. So the model having to figure out that, hey, I need to go back and calculate the loss, how far am I from the expected output, and go back and update the parameter so that next time it could be slightly better. After you do that for a few or millions iterations, the model become really good. So imagine that our input is not these four numbers. Our input is embedding vectors. That's it. That's as simple as that. So our input is embedding vector of the words of the sentence. And you try predicting one single number with each sentiment, 0 or 1. 0 means negative, 1 is positive. That's it. That's really cool. Like deep learning is just like that. Okay. Of course, I'm trying to simplify that, but you know what I mean. So here are the real life example of the deep learning. So you have a picture of the numbers, 784 pixel, right? And each of the neuron here try to predict things, try to extract features, different color here are predicted by the, okay, let's try to do that again. So each neuron here try to extract one of the color here, right? And then the neuron in the next layer gonna combine the feature instructions from the previous layer, so can detect something more complex. And at the end of the day, it try to predict is it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. That's it. And you can see that at the end, it's light up at the number 9 here. So predicting that is the digit number 9. Come on, do it. Boom, number 9 light up. Okay. So as simple as that. It's going to be very similar to our sentiment analysis. Yeah. All right. So this is gonna be a demo time. I'm gonna give you guys a break soon, very soon. Yeah. So stay tuned. So this demo gonna be a sentiment analysis program in TensorFlow using TensorFlow keras that gonna identify whether the movie review is positive or negative based on the text. And you know that TensorFlow is developed by Google. It provides low-level tools that can build and train neural networks. And also support all the things that we need for today. And keras, I talk about keras. Keras is a high-level API for TensorFlow that make building neural network is so damn easy, right? With keras, just a few lab code and that's it. That's why we love keras. So today we're gonna learn how to use TensorFlow keras to build our first neural networks to predicting the sentiments of a text. All right, here's the links. I know that you guys love cool tech, so I already included in the QR code. Yeah, so try that. Or you can enter these links inside your browser. So please type in these links into your browser. I give you guys like 1 minute for that, or you can scan the QR code, you know, to be trendy. Okay, I give you guys a good 5-minute break, yeah, and then we come back for this. So make sure that you open these links and ready. You open this link and you choose to open with Google Colab. Okay, that's very important. You need to open this and open this notebook using Google Colab. That's it, and you can go for a break for 5 minutes. Okay, we have 10 million questions in the chat. I wish I have a machine learning model to figure out what is the most relevant questions. Okay, let me repeat that, guys. 80% of the people in the chat asked me that will the lecture slide and material will be shared? Yes. So you can see that this is the link for the lab, all right? And that's it. And then for the lecture slide, I will share with you guys in the chat right after the workshop finish. Okay, if you want to have the links of the lecture slide, you have to wait until the end of the workshop. Okay, it's kind of a trick to hook you up until the end of the lecture of the workshop, but okay, so there are two links. We have one link for the lecture slide and one link for the workshop lab. Okay, only two links. And you have one link already right here. So try your best to open this on the browser. Okay, I'll be back in 2 minutes. Okay, so if you are looking to the links, maybe you will see that there is option to open with the Google Collaborator, right? So click to that. Okay. Okay, can you see my notebooks? It's interesting. Can you see my notebooks? Put in the chat if you can see my notebooks. Okay. Um, Let me share this again, just in case that you can't see my notebooks. Share screen. Okay. All right. So there are two stages of these notebooks, right? The first stage and the second stage. We're gonna have a quick tutorial about what is how to do the symbol tokenizations in TensorFlow. Yeah, very interesting. And so also the basics of word embeddings. Okay. Give me a second to double check. I remember I have a newer links for the I'm gonna share on the chat. Give me seconds. Double checks. Mm-mm-mm. Okay, so this is the new links. I'm gonna share in the chat. Two. Okay, copy the links, and I gonna copy into the chat. Yeah, 2 seconds to the attendees. Okay. All right, guys, that's the new links, but don't worry about that. For this today workshop, I don't require you to follow me at all. I actually require you guys to like try to go through with me. Yeah. So there's no exercise, whatever. Right. The course is done for you guys. I think it's more important to understand line by line and the concept. Okay. So this is the sentiment analysis with TensorFlow. Okay, there's two stage. The first stage and the second stage. Highly recommend you guys to go through the first stage. But everyone, for the people who are already expert, right? You can go through the second stage. Okay, let's go for the first stage. For the first stage, we have four ID we want to learn. The first one is tokenizations, right? You already kind of know about that. Tokenization is like try to convert a text into numbers, and then after you got back that got back the dictionary, mapping the word into numbers, you want to convert the whole sentence into numbers. Later on, you want to do padding because you want all the sentence to be in the same length. And I will explain how can we do the embedding factor layers. These are separate tutorial, really cool. And after you go through all of that, you're gonna go through the stage two, which is how to build a sentiment analysis neural network model from scratch to do the IMDb sentiment analysis. I already prepared this notebook so that you don't need to have me to explain to you guys later on, right? Let's say you want to go home, you want to self-study. It's there, right? All the comments already there. Uh, so I prepare the best I can for you guys to like study by yourself. Okay, but we're gonna go through this regardless. Okay, let's go through tokenizations. First, let me zoom in for a bit, in case people can't read that. First, I want to import the TensorFlow and TensorFlow keras. I assume that everyone must know Pythons by now because the first challenge quite challenging if you don't know Python. Okay, so run that. Okay, there's one thing I need to remind you guys. The first step when you open a Jupyter notebook is this notebooks belong to me. So if you want to make a copy, you have to click to 5, save a copy in the drive. And if you want to run a cell or code, you can click to these buttons, run, play, or you can press Control Enter, Shift Enter, sorry, to run that code. To make things run faster, because at the end of the day, machine learning model require GPU. You go to runtime, change the runtime type, and put the GPU there. By default, it's run on the CPU. Gonna be really slow to train a model. Okay, so let's do that. First, make a copy of the drive. Do that. Okay, let's do that. Why not? Everyone, please do that. Make a copy of the drive, and then connect to the server in Google. The cool thing about Google Colab is we don't need to install any library on our computer. We actually borrow a server in the Google to run our code, right? It's really nice. And then you want to change the runtime type to GPU. Perfect. It's already in the runtime GPU. So my model gonna run really quick. Okay, let's go through this first step. I want to import TensorFlow keras. Okay, guys, don't need to live code with me. Just listen to my lectures. I think it's more important. Second step is import the tokenizations. Okay, so this library gonna help you to convert a word into numbers. Okay, let's consider we have two sentences. I love my dogs and I love my cats. Noticing that we have a different capitals here, I here in the lowercase, I here in the uppercase, and we have these comma, these. So at the end of the day, for the traditional machine learning, we need to take care of that, right? But the cool thing about TensorFlow is cleaning the data. Cleaning the data is all done for us. I'm gonna show you guys later. So this is our sentence. We have two sentences. And when you want to create a new object called tokenizers, and with attribute numWords equal to 100. NumWord is the maximum number of words we're gonna keep. For example, we have two sentences right now, but it's okay. But imagine that we have 100 of books to tokenize, and so we have 10 million unique words, right? So it's impossible to store all of that into our computer anyway. So you want to limit the amount of work that our tokenizers gonna take. So let's say you put the number equal to 100, then you only want to keep 100 words to be tokenized. Okay, for example, this. And then you want to, there's a method called fit on text. Fit on text is the method that learn how many unique words in the collections, and then gonna figure out what is the frequencies of the word appear. Sorry, run this. Okay. Now tokenizer got all information regarding how many words inside your collections and the frequency of the words. So when I want to check out how many words in my collection, I can do tokenizers dot word index. Okay. All right. So can someone get, this is a question for you guys. So please put in the chat if you know how to answer the questions. Can you guess why some specific words got small index number? Let's say one here. So, sorry, I here is 1. And some word got a high index, like cat is 5. Is it based on alphabet order, or is it based on what? Can you put in the chat? What word that is determined to be a high index, like 5, and what word that is determined to be low index, like 1? Can you put in the chat? Yes, I saw a lot of people got the right answers. It depends on the frequencies of the word. For example, you can see the I here are 1. Why? Because you can see that I appear twice. It's the highest words appear, and next one is I, also 2, right? It's low index. But for the word that appear once, like cat and dogs, put a high numbers index. We can try that, right? We're going to try that, put that into you. Okay, let's put love. Love twice. Let's put love twice. I love my love. Okay. So now we're expecting love to be index 0. Yeah, index 0. Try that. Sorry, 1, yes. So love now got a higher index. Because why we are doing this? Why the TensorFlow doing this? Because at the end of the day, the word appear a lot, going to be converted into numbers. You want that word appear a lot, got a low index, because imagine that we have 10 million words, right? And the word appear a lot like I got like a high index, like 9 millions. You cannot have 9 millions everywhere. You don't want that. You want to keep a small memory. So that's why you want the word to appear in the high index, got a small, sorry, the word appear a lot, got a small index, so that you can have these tokenization small, right? This memory of tokenization small, okay? So that's the idea of why some word that have a high index, some word have a low index, correct? Okay, so this is dictionary. So you know that one gonna map to what? So I gonna map to 1, love gonna map to 2, mine gonna map to 3, and cat gonna map to 4. Okay. Okay. And let's consider this example that, let's say we have some exceptions like exclamation mark or these weird characters. Usually in other traditional machine learning, you need to figure out that, hey, you need to clean them up. But the cool thing about tokenizations of the TensorFlow is it's already done for you. Okay, let's try that. So if you run this and want to print out the word index, you can see that it's lowercase everything for you already. Nice. And also it's removing the letter that is not important, like exclamation mark and these characters. So you can check out the documentation of tokenizers. You can see that these are the filters of the tokenizer. It already removed for you. So if you want to remove all the special character, you can just define this attribute again and put the special character you want there. As easy as that. Okay, so now you see that how the words can be tokenized and TensorFlow handle that for you. You have the word index. Now you want to change the whole sentences to the numeric tokens. So let's do that together. Um, okay. All right, so let's try a different example. Before we have only 2 sentences, now we have 4 sentences. And you can see that this sentence are a bit too long, right? Do you think my dog is amazing? You love my dog, okay. These sentences are just an example, right? Pretty silly. And then we're gonna apply the same step again. So we're gonna create the object tokenizers with the number of words, 100. This one up to you, right? Depends on how much memory you can take it. And then you're gonna fit on the text you want tokenizer to learn number of unique words in the text and also the frequencies of that. And then using that dictionary, you want to show you dictionary first. Bring out dictionary. Yep, this is the dictionary that you have. This mapping, right? Which word to which tokens, and then you want to convert these sentences into text by using the method text to sequence. That's it. Gonna create a sequence of tokens, right? So we have I love my dog, I love my cat, you love my dog, do you think my dog is amazing? Okay, let's try that. And print out sequences. Wow, okay, you have this. You have 4 sentences and you have exact back 4 sequence. Yeah, exact 4 of them. And the first sequence is 4, 2, 1, 3. Okay, can we make sense of this? Can we decode this? 4, 2, 1, 3. 4 is I, 2 is love, 1 is mine, 3 is dog. Easy, right? This is the first sentence. I love my dogs. Okay, too easy. I love my dogs. Okay, now our sentences from text into numbers. Beautiful. So the question is, what about the works that your model haven't seen before? Let's say I want to have a test data, like really, there's 2 works here, really and food, really and food. Are the 2 new works that my model haven't seen yet, right? So with our fit to text, I'm gonna apply the text sequence right away. Keep in mind that my tokenizers object haven't seen the work really input yet. What will happen? All right, you can see that it's actually removing that word, right? For example, I love my dog. This exactly return back to I love my dogs. It's removing the token really, or the word food here. Okay, it's got what? 1, 2, 3, 4, 5 sentences, but give back only 3. Why? The word loves haven't seen it. The word food haven't seen it. So that's why removing these 2 tokens. Okay, so you are thinking, hey, that's disaster, right? So you don't want to do that. You want you don't want the sentence to become shorter and shorter. You want to keep the same length of the sentence. So how can we do that? So the trick is you're gonna using attribute called OOV. Can anyone guessing what is OOV stand for? Anyone, please, can you guess what is OOV stand for? What is OOV? Object, I don't know, I try. OOV, what does it stand for? Correct. It will be out of vocabulary, right? It means that I don't know that word. So at the end of the day, right, you can put anything you want. You can put Tom here, but you have to make sure that the word Tom here would be never appear in your documents. Okay. So when you put bracket OOV bracket, you're pretty sure that this word might never appear in your text. So you can be replacing every single things of that by this word. Oh, perfect, right? You can put your name here or put your girlfriend name here. I don't really care though. So put OV by conventions. And let's try again. Let's try that again. You have the test data here. And in this case, we're gonna fit the data against. Right. So you can see that now OOV is index 1. Okay, so can anyone tell me why OOV is index 1? Interesting. We know that low index usually reserved for the highest frequencies of the work, right? But OV, why OV is index 1? Can someone type in the chat? Why OV's got the index 1? Why got a low index? Yeah, so some people answer them correctly, right? Because the model assumed that, let's say there are 10 million different English words in the world. It's assumed that it's only know up to 1,000 words, right? The most common 1,000 words. And when it comes to the unseen data, it's assumed that there is a lot of words that you haven't seen. So a lot of words will be OOV. So by assuming, it say that I assume that when I'm predicting the new data, there will be the most work which I don't know about. So I put the index reserved for OOV is 1. And it makes sense, right? And you assume that what you know is so little and what in the world is so big. So you don't know everything. But now the question is people asking like, oh my God, Tom, why it's not 1, sorry, why it's not 0? Because Python love to start everything with index 0, right? Have you ever asked yourself that, right? Why not 0? 0 actually reserved for another purpose. Wow, it's got a lot of blocks, you know. So 0 reserved for another purpose. I will explain about that later. So now OV now. So if you run the sentence again, you can see that the words really is not seen by the tokenizer before. So it's put that to be 1 here. And the word loves haven't seen by the tokenizer before. So it put 1 here. And the word food haven't seen by tokenizer before. It put the word 1 here, right? Because it's OOV, not seen before. Okay, it's ready, right? It's good. So now all the sequence will have the same length of the original sentences. Pretty neat, right? Pretty cool. But the problem there's another problem that our model can handle sequences with different length. But when you train the images, right, you know for sure that all the images have to be the same size. The same thing with our sequence of tokens. We require them to be in the same length. And you know that based on our original data, the first sentence only have 4 words, 4, 4, and you have 6 or 7, right? This is the longest. So you want all the sentence will be in the same length. That's what we want. We want consistent across all the sample. So we need to figure out how to do paddings. Padding is like put a bunch of zero to make everything the same length. For example, you have a sentence here, and you apply your tokenizers again. This is the same step, right? And then you convert your sequence into numbers, sensible. And now you are applying path sequence. So for people who want to know about path sequence, you can click this link. Path sequence is really straightforward. That's it. Okay, path sequence 35. I need to run this and this. Okay, as you can see that it tries to figure out what is the longest sentence. This one, right? There are 7 words in this sentence. That's why it tries to make every single sentence to be exactly the length 7. 7 here, 7 here, 7 here. And you can see that it achieved that by adding a bunch of zero into the short sentence to make it the same length. Okay. Now the question is, hey, this padding at the beginnings, right? What if I want to pad them at the back? You can do that, right? Easy. You say padding equals to post. The word post here actually is similar to the word postgraduate. This means that you study master after you study bachelor's, right? Post means after. Can anyone guessing what is the word before? Before. After mean post. Before mean pre. Yes, correct. Preschool mean kindergartens, right? So technically, you go to preschool mean you go to something before you go to school. So preschool means kindergartens. So by default, it actually pre. Okay, but you want to post them at the end, so that's why you say post. Okay, now it's padding at the end. All right. So which one I recommended? I would recommend padding pre. Why? There are some model that like RNN and SDM refer you to have information at the end of the sentence, right? Because if you put them at the front and then you feed them garbage later on, it's actually forget what's going on before that. So if you put them garbage before and then you put them the important information later on, the model actually can remember that. So technically, I recommend using pre, but it depends on the model. So we don't have time to go too much about this. And then let's say you are not happy with the length 11, right? Because length 11 is the longest sentence. And sometimes you might have a sentence really long, like maybe 4 paragraphs, right, of the review. You don't want that. You don't want every sentence to pass that long. If that costs so much memory. That's why you want to remove that. You want to truncate that. You want to set a maximum length. Let's say 6. Now the question is, you know, cut off some things, right? You want to cut off at the head or at the back by applying truncate, post, or pre. Post means you cut off at the tail, at the back, and pre means you cut off the sentence at the front if the length of the sentence above 6. Yep. So now you can see that it's posting at the back is try to keep the sentence to be 6 and it's cut off at the back. The same thing here, pre mean is cut off at the front. You can see that it's off. This, you have this later on here. It's cut off at the end. The front, yes. So yeah, you can play around with different settings here and to see which one actually give you better models. Now you have convert them to be really ready for your models, right? These are like really juicy already. Now the next step is these are numbers, and remember we're discussing about number are not good because number gonna treat every single word independence. So you want to get some meaning, you want to describe some relationship between each of the tokens, right? So you need embeddings. Okay, so let's go through embeddings. Okay, I think I might able to do it before 8 p.m. in Vietnam. Yes. So let's look at these two examples. I love you and I will be ready. After you convert them into tokens, look like this, right? It's a big numbers because in this example, we assume that we have like 100,000 of different unique words, right? So this tokens is decent, right? And the zero here because padding, right? So but by now you know that the max length is 5. Okay, every single sentence has the same length, which is 5. So these two sentences convert into the sequence of tokens here. Now the idea of embedding layers will be after you apply the embedding layers, you're gonna get out the work embedding vectors corresponding to that tokens. For example, this 1, 2, 3, 4, 5. Now give you back exactly 5 different word embeddings. The same thing here gives you corresponding 5 word embeddings representing for that meaning of the words. Okay. Okay. So let's try that. We have 4 sentences here. Okay. You apply the same step again for tokenize, fit to text, word embeddings, and text to sequence. You apply that. And now you want to print out the word index. We have exactly, okay, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 words. But why do I say 12? Can anyone in the chat say, answering why I mentioned there are 12 tokens, not 11? There is 11, right? What is 12? Why I mentioned that there are 12? Correct, because 0 is reserved for paddings. So that's why you need to consider 0 as well. So in total, we have 12 tokens from 0 to 11, exactly 12. So let's print out the sequences. This is the sequences that you have. And then you pass the sequence. Okay, and then you take the shape. The shape is 4, 6. Why? You have 4 sentences, and you mentioned that the length, maximum length of these sentences is 6. So the shape of your padding sentences will be 4, 6. Okay, makes sense. And then try to get out the first sentence. Let's see, the first sentence will be, the first sentence here will be 5, 3, 2, 4, 0, 0. Okay, straightforward. And you can decode that. So 5, 3, 2, 4, 0, 0 will be I love my dogs. Okay, and then 0, 0 is padding, clearly. Now let's talk about the important stuff, which is embedding layers. So to do that, you import new library called layers. Okay, layers. So in this case, we want to define our vocab size with 12. And this embedding, so 12 is exactly 12 tokens I mentioned just now. And embedding dimension will be 3. So this one is totally up to you. I told you guys already, depends on the size of your data set, right? So the bigger your data set, the higher dimension you can choose. So in this case, we only have what, 4 sentences. So let's choose something really small, like 3. Okay, so it could represent for good, bad, or crazy. Okay, for example, and you want to create the layers for that embeddings by put in the vocab size and embedding size. This one technically create a matrix, a 2-dimensional matrix with the size, vocab size by the embedding dimensions. So sorry, I'm losing my voice. Okay, let's bring out the input dimension and output dimensions here. Okay, I need to run this. Okay, it will be 12, 3. So why 12, 3? It makes sense, right? Because we have 12 unique words in our vocab, and each word representing by 3 numbers. So that will be 3-dimensional vector. So the size dimension will be 12, 3. All right, that's really straightforward. So to So if you want to get all the layers from that embedding, you can do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This assume what? This assume that this sentence got every single token inside my sentence. That's why I can retrieve all the embedding vectors like that. It takes some time. Okay, so you can see that these are the full numbers of my embedding layers. Okay, now let's apply for example and sentence would be 0, 1, 2, 1, 2, 3. That sentence would be, okay, let me print out the word index. So this sentence would be, let me decode that. So 0 is, okay, padding, 1 is OV, 2 is my, 1 is OV, 2 is what? 2 is what? My, and 3 is love. Okay, these sentences are pretty boring. Okay, so if you apply this sentence into the embedding layers, you get back what? You get back exactly the, each of these tokens gonna return you back the word embedding vectors corresponding to that. So that's exactly what you get back, right? This is beautiful, right? It's so simple. The code is so simple. Okay, so let's try our first sentence of the, remember this is mean I love my dogs, right? This is the sentence, I love my dogs. The length of the sentence is 6. Okay. Now you can put in the first sentence inside your embedding layers, and let's print out the result. 63. Okay, the size of this embedding layer is 60. Why? Because, okay, I need to, okay. Why? Because you have 6 words, and each word representing by 3-dimensional layers. So the size is 63. All right, so let's do the hardcore things that we put in our full preprocessing data into our embedded layers. So let's check the size. Can anyone tell me why the size is 463? This is 3-dimensional array. It's pretty long. So can anyone make sense of this in the chat? Okay, let me share the code and the slide right now because people in the chat want that. Links, copies. Okay, I put the code in the slide right now. So that is the code. And for the slide, share. Okay, that's the slide. Okay, just in case people hungry, need to go for dinners. Okay, so can anyone tell me why the shape of the output for the whole padded sentences would be 469? So 463. You have, correct. So you have 4 sentences. You have 6 words in each sentence. Each word represented by 3-dimensional layers. Vectors, sorry, that's it. That's why you have 463, and then you're gonna plug this into your model, and it works, right? Correct. You guys are very smart. I'm really happy. All right, so you went through the basics understandings of NLP in TensorFlow. So now let's do the real things. Trust me, the real thing take nothing. Okay, there are 2 steps: prepare the data and train the model. That's it, guys. And I have some extra model for you to play around with. Okay, you can check the menu here to play around with. Okay, so let's open the data. The data is already prepared for us, guys. These are classic libraries for you to enter. And now you already can make sense of these parameters, right? And feel free to tune your model by changing these parameters. So your vocab size is 10,000. This is our max vocab size. And our embedding dimension will be 100, right? Because we know that we have 25,000 reviews, so that's a lot. So let's put that to be 100. And the maximum length for each sentence, let's cap that to be 100. Because I feel like if I read the first 100 words of the review, I already know that that review is positive, negative. Okay, because at the first sentence of the review usually telling you what is the feeling of the person, right? Oh my God, this movie is horrible because blah blah blah. Oh my God, this movie is so good because blah blah. So I assume that the first 100 sentence already telling you the sentiments of the movies, of the review. Okay, so chunky tab post, padding tab post, and this is your tokens of OV, and you have around 20,000 training size for the reviews. Okay, let's try that. And for the data, we're gonna download it from the TensorFlow dataset. This is really nice. While waiting for that to download, you can have a look at what is the other data set for you to play around with. You can see here, it's huge, right? We have audio, we have graph, we have image classification, we have object detection, we have structured data, we have text, we have videos, we have everything here. So this is the data we download from TensorFlow, IMDb reviews. You can go through this. This is quite interesting. We are using the plain text from the TensorFlow. Another thing is when I download this data set, it's already shuffled for me. It's already split the data for me for training and for testing. And you can have a look at how many for training and how many for testing. For testing, 25,000 and training, 25,000. Perfect. Okay, you can get all information you want from these documentations. Okay, so it's done. And then this step allows you to get back the training data and the testing data. So let's go through that. We don't really have time. Don't worry about that. This one is kind of like a small processing for you to convert all the string into really a string, okay? And put them all inside this for array. This is the for array we actually care about. So let's bring out the training sentences, 25,000. Okay, perfect. And we can bring out some example of our data. For example, this movie is absolutely terrible. Okay, that's definitely zero, right? Negative. I have been fall asleep during the movie. Okay, clearly, right? I told you guys, the first sentence always telling you what is the sentiments of the review. Zero. What this kind of movie falls no blah 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 blah. Wonderful performance. See, the second sentence or telling you that this person have a positive review about this movie. So label one. This movie seen by blah 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 suffer from eating disorder because so amazing accurate. Okay, positive label one. Okay, so this is for example of the movie review we get from this data. We have 10 minutes to wrap this up. Yes, let's do it. So we have these things you got all the expert of, right? We have tokenizations, we have fit on text, we have word index, we have transform the sequences to the tokens, and we pass the sequence. We want to do that separately for training and for testing. Why? Because at the end of the day, you only want to apply the fit to text only on the training, yeah, or not for testing, because we assume that the model only see the training data, not the testing data. So that's really careful. Be careful about that. You don't want leaking the data from testing into the training. There's a whole theory about that. I'm not gonna go through that. It's gonna take another 2 hours. Okay, so make sure you remember that when you train on stuff, you make sure that the model only see or learn on the training set, not the testing set. And then this is the function to convert back from tokens back to the original text. For example, this is absolute terrible movies, blah blah blah, and then I tokenize them to be this. With these paddings. Okay, this is weird. I haven't run this whole thing yet. Okay, let me run this whole thing real quick. Yeah, I haven't run that thing. Oh yeah, so if the collapse shows that the line is hidden, you need to open that, right? Click here to open that. Click here to open that. Someone asking that on the chat. Okay, so we have the original sentence here, and this is the tokenized versions. Okay, and after we reduce that into exactly 100 words, it looks like this. And after you report that, you have this. So there's a few words already OV because you see that in the training, you don't see that for the testing. So it gives you OV. And the label for this one to be 0, mean negative. This is absolutely terrible movies. Okay, that's definitely 0. Okay, so make sure that you went through and convince yourself that this is ready for your training. Okay, I need to this is function to plot the training and the accuracy after the training model. And to open that link here, yep, open that. Okay, so let me quickly go through the ideas of machine learning here in 2 minutes. Okay, so the process of training your model have only 4 steps. While I'm training, I'm gonna run this first. It takes some time. So there's only 4 steps to do machine learning, right? The first one would be the forward propagation. This means that you plug in your work tokens of the sentence, and the output would be the sentiment, the result. At first, when you just train your model is pretty bad. It gives you the wrong output. So you compare the output to the expected output, the labels, to calculate the loss functions, to measure how bad is your output of the model. And then after you know how bad, you can do backpropagation. It means that you're gonna calculate how much you need to update your parameters in the model. So that the next step, when you do forward propagation, would be better, right? And the fourth step would be kernel descent, mean that you actually take the value that you learned from step 3 and you update the parameter in the model. That's it. These are the 4 steps. I swear to God, every machine learning in the world will follow these 4 steps. Okay, so technically, that's it. Doesn't matter how complex machine learning is, they only have 4 steps to follow. So after training your models for many iterations, your model gonna have a good parameters and achieve the high accuracy and low loss. So you have a step here. This is the very simple step to define the structure of your models. You can see that sequential mean the layer gonna be next to the layer, be next to the layers, and you want to put in the embedded layers. Remember, this is the one we want. We want to convert every single tokens into embedding vectors. And from that, you want to flatten them. You want to put them all together into one single dimension to keep it simple. And then each of the numbers is going to connect to A neurons. There's A mean A neurons. And lastly, you want to get out one single number. This number is now representing the sentiments for the models or not. So this step, defining the model, right? Defining the model allows to do the step 1 for propagations. And then you need to define the loss. The loss is telling you the loss function, how bad is the output compared to expected output in step 2. And then you define the optimizers here, Adam, right? Because Adam is a function telling you how to update the parameters in step 4 here. Okay, so everything makes sense, right? It's like you have 4 steps and you try to plug in what you want for each step. And you want to show out the accuracy, how good is your model. If you leave this, that's fine, it's gonna work as well, right? I want to show the accuracy. So after my model train, okay, this is train part. To train a model, you only do model.fit. And you put in your, remember, this is your train data, padded. And this is the labels, right? This is the expected output. And after training for 10 epochs, I mean that you're gonna go through the whole data set 10 times. And validation data is like, after every single epoch, you're gonna use the model and test again unseen data to see how well is the model. So at every single step, you can see that it's telling you what is the current accuracy, right? At the first epoch, horrible, it's only get 67% accuracy. And later on, it's get up to 99% accuracy for the training. Really good. But for your validation, it's unseen data. So your model couldn't do as good as the training data. This is your accuracy for your unseen data. So I'm gonna let it train for a bit. You can see that it's actually measuring how fast it's run for every single epoch. It's run really quickly because I turn on the GPU. So if I don't turn on the GPU, it's gonna train around 8 times as slow. So always remember to turn on the GPU to 7 your times. Let's train that for, come on, 10 times. You can see that the accuracy for the training data was like 100%, right? It's like, oh my God, this model predicting every single sentence in the training data perfectly every time. But for the unseen data, because it's have a lot of work haven't seen yet. It's get up to 82% accuracy. Honestly, as a human, I'm happy with 82% accuracy, because imagine I have someone to read all the 25,000 review and figure out is it negative or positive. It takes forever. I refer this. I refer only take me like what, 1 minute to go through this 25,000 reviews in the crazy accuracy. I can plot out the accuracy and loss. We don't have time to explain about this. Okay, so this is, you can try out your own example here. So for example, I put in 2 sentences here. I think this is really amazing, honest. It sucks so bad. So these are 2 sentences. I apply the same process that I go through the preprocessing part, right? And then I do model.predicts. That's it. That is how you are predicting the sentiments for the unseen data. So these are the 2 sentences. These are the 2 sentences after pattern. And I get back 2 numbers here. So the first sentence give me 0.9. What does it mean? Remember, 1 is positive. So it gets really close to not, so 1. So it means that my model successfully predict that the first sentence is positive. And it sucks so bad is 0.01. Remember, close to 0 means negative. So my model successfully predict that this sentence is really negative. Okay, so my model worked perfectly well for the unseen data. We have 3 more minutes, guys. And for fun, we're gonna do something really cool here. We're gonna export our embedding layers that we have over here, right here. We're gonna export all numbers here with all the words, and then we're gonna plot them into, so you run these functions, and you run this one, and eventually it's gonna download 2 files for you. One is vector TSV and one is meta TSV. So meta content, let me quickly open that. So meta content all the words, right? All the words. And vector TSV contain all the vectors that corresponding to each of the words. That's it. And then we're gonna open the we're gonna open this website and gonna plug in our 2 file. You can see that this is the one that trained by people. So I want to plug my old data in, right? So there's 2 files. One is TSV. So I should upload the vectors. Come on, vectors. So vector TSV here. Yep. And one is determine what is the word for each of the vectors. So I upload the meta. So the meta TSV here. Yep, perfect. Okay, so look out here. So this is in 3D. In the 3D, it's pretty hard to see. So let's make that into 2Ds. And now I can search for the word, right? So I put in the word. Let's say wonderful. All right, wonderful. Come on. And I can see that wonderful is on one side of the graph. And then I put in the word horrible. You can see that wonderful and horrible on extreme 2 spectrum of the graph. So my model actually learned how to figure out what work is actually really positive and what work actually negative. You can try that with the word excellence here. Try it with the word excellence. Excellence. Okay, the same result again. So I'm pretty sure you can go home and try different works here and just figure out, hey, what work in the middle here? The work, okay, sorry. The work in the middle here are actually neutral. It doesn't really tell you that it's positive or negative, right? You can go around here and say, hey, these work in the middle have absolutely 0 sentiments. Okay, for my model. Okay, so that's pretty cool. So let's quickly wrap up the, okay, where's my slide again? This one, yep. Let's quickly wrap up the things. Okay, so all right. So thank you for your listening. Before we leave, I want to have a quick talk with you about. Okay, so you can see that sentiment analysis is really cool. So sentiment analysis can apply for countless aspects of the business, from brand monitoring to the products and analytics, right, to customer service and market research. So it's have moved from a very interesting high tech to a very essential tool for all the company in the modern age. And the technology is so involved that it's so effortless and it's too easy to implement the machine learning deep learning model for that. Actually, it's the best time for you to learn machine learning and data science right now because there's so much data available and there's so much potential of this technology. Of this technology can change the world and make the world a better place. Thank you very much for your listenings. I know you guys are really curious about this technology, so I also include a few extra data sets for you to play around with. We have a Twitter airline sentiment on cargo. We have the Amazon product review on the sentiment analyst. We have the product reviews. We have the IMDb movie reviews. We have the Amazon 5 food reviews, right? These you can download the data set and apply the same method that we learned during the workshop and get the sentiments out of it. And also for the people who actually curious about, hey Tom, I want to know more about natural language processing or machine learning or deep learning in general when it comes to that. How about I want to know more about word embeddings. I already including extra material for you to learn TensorFlow on the TensorFlow website. So this link is for word embedding, this link for word to vec, and this link is you're gonna using the extra model to classify your sentiments. Remember, in our models, are including extra model for you to play around with. 1, 2, 3, 4. All right. So I including 4 extra model for you to play around with. So I hope that you guys actually take your time to look into this and learn what is different between different models here. Um, oh yeah. So thank you for your listening. Really. So is the feedback links that give me a feedback, please.